Welcome! Our goal for this video is to use Lewis theory to determine the connectivity of our molecules. And we can try to identify the types of our bonds and the number of lone pairs on each atom in those molecules. By this point in our chemistry careers, we have a pretty good idea of how our atoms are organized. We know about our nucleus, our protons, our neutrons. We know about our electrons and the orbitals that they exist in. Our next step, though, is to start to combine these atoms together to form molecules. We want to learn all about how our atoms bond together, what types of bonds we have, what shapes we can form, because these affect the characteristics of our molecules. To accomplish these goals, we're going to focus on Lewis theory. It is not the only theory of bonding, but it's a good starting point for us in this class. In Lewis theory, we only have to consider our valence electrons. These are the outermost electrons, as we remember, and we can shortcut the number of valence electrons based on the column in the periodic table. In our Lewis dot structure, we can draw these valence electrons as dots. We can surround our atom with these dots to show exactly how many valence electrons are there. For our individual atoms, we have a few rules that we get to follow, and we can see some examples here and on the next slide. We can look at our individual atoms and decide if those atoms are stable or not. In order to be completely stable, our atoms want to have an octet of electrons, 8 valence electrons. The exception is hydrogen and helium and lithium. Those are happy with 2 valence electrons. Every other atom is going to want to have 8. If we take a peek at this oxygen, it only has 6 valence electrons. That's not enough. It's not going to be satisfied right now. So it's going to have to form some chemical bonds. Chemical bonds occur when we're able to share electrons between atoms or steal electrons from another atom. Ionic bonds occur when we're able to steal those electrons, transfer them from one species to another species. Covalent bonds are when we're able to share electrons. In this chapter, we're going to focus on our covalent bonds, sharing electrons between atoms. These covalent bonds, as we said, are electrons being shared between atoms. We do that so that both of those atoms can obtain the octet, or perhaps duet for hydrogen, that they want. Each hydrogen in our molecule would like to have 2 electrons, and our oxygen would like to have 8 electrons. This is that octet rule. Unfortunately, right now, hydrogen by itself only has 1 electron. Oxygen by itself only has 6 electrons. In order to achieve that octet, we're going to need to start to share Once we start to share, those hydrogens can gain access to some of the oxygen's electrons. Meanwhile, our oxygen gains access to those electrons from hydrogen. This is a win-win. Our hydrogens now have 2 electrons each, and our oxygen now has 8 electrons, just like it wanted to. We have some terminology we can introduce. When electrons are being shared between our atoms, we can call this a bonding pair. That bonding pair can be drawn as 2 dots, or more commonly, we can draw it as a line. Each of those lines is the same thing as 2 dots. A dot is 1 electron, a line is 2 electrons. The other term we can use is lone pair. A lone pair is a pair of electrons that is only on one of our atoms. When we are forming these molecules, our goal is to get up to an octet on every single atom. We saw for water that involved sharing electrons with a pair of hydrogens. We can also share more than one pair of electrons. We call this a double bond or a triple bond. Here, our O2 molecule has 2 lines or 4 dots. There are 4 electrons being shared between those 2 oxygen atoms. When we're able to do that, each of those oxygen achieves the octet. In order for N2 to form a happy molecule, we need to share 3 pairs of electrons, a total of 6 electrons being shared. We call this a triple bond. The more electrons that are being shared between 2 atoms, the stronger that bond. And the stronger that bond, the shorter that bond is. Our plan now is to introduce a strategy for figuring out what our molecules have to look like if they're obeying this octet rule. We have a 6-step strategy. First, we can decide what atom is in the center, what atoms are surrounding that center atom. Second, we can decide how many electrons we have to work with. Count up all the valence electrons that are present, and we'll use those valence electrons to build our molecule. Third, if we're going to follow that octet rule, we have a math trick that we can do. We can figure out how many electrons would be needed or wanted if our atom was to achieve that noble gas octet without having to share anything. We can subtract number 2 from number 3 to figure out how many electrons are shared. We can subtract 4 from 2 to find out how many electrons exist in lone pairs. Lastly, we can fill in our electrons into our picture, make sure that everything is connected, use up all the bonding electrons we decided that need to be in there, and then add in our lone pair electrons so that every single atom has the octet. This is a lot of steps, but we'll do an example and see how it looks. Our example is carbon dioxide. Carbon is always going to be in the center, which means our oxygens get to be terminal on the outside. Step 2, we can figure out how many valence electrons that we have. Using the periodic table, carbon comes with 4 valence electrons, oxygen comes with 6 valence electrons, and our second oxygen also comes with 6 valence electrons. The next step, we can figure out how many electrons we would like to have if we weren't doing any sharing at all. Basically, every atom wants 8 electrons besides hydrogen. Carbon would like the octet, oxygen would like the octet, the other oxygen would like the octet. If there's no sharing at all, we would need to have 24 electrons. Step 4, we want to do some subtraction. We'd like to have 24 electrons, but we only have 16. Our math trick here is the difference is going to be the number of electrons that have to be shared in the form of bonds. Our last math step, we have 2 options for our electrons. We can either be lone pair electrons or bonding electrons. Well, if we have 16 electrons total, and 8 of them are in bonds. The other 8 of them have to be in lone pairs. Step 4 and step 5, these are the numbers that we actually want and care about. These are the electrons that we're going to fill in to our picture. We can fill in our bonding electrons by first making sure everything's connected. Those 2 lines count for 4 electrons. We want to draw 8, so we need another 4. There's no place to put them except maybe we can double up here. Maybe we can double up here. There's nothing else that needs to be connected. Now we can start building double or triple bonds. Four lines is 8 electrons. We've filled in all of those bonding electrons. Our last step is to fill in our lone pair electrons. We want to make sure that every atom has the 8 electrons that it wants. Carbon right now, it wants 8 electrons and it has 8 electrons. No need to do anything else. This oxygen wants to have 8 electrons, but right now it only has 4. This is not good enough. We need to add another 4 electrons. Our last oxygen also wanted to have 8 electrons. Right now, again, it only has 4. We're going to need to add more electrons until we get up to the 8 that we wanted. There we go, our 6 steps to end up with a molecule that follows our octet rule. I'm going to erase this little Venn diagram. This is our final answer. If you want a way to check your answer, double count and make sure that you have the total number of electrons correct. We started with 16 electrons. We should have 16 electrons in our picture. And we want to have an octet on all of our atoms. We can double check, make sure each atom has access to exactly 8 electrons. A second example, we have NO2-. This is our friend nitrate. We can start by counting up the valence electrons in our atoms. From the periodic table, oxygen comes with 6 electrons, nitrogen comes with 5 electrons, oxygen comes with 6 electrons. It looks like we have, 17 electrons, but don't forget this -1 charge. That -1 charge means we have an extra electron. So we get to have a total here of 18. Next, we can start to do our little math tricks. We can decide how many electrons we want. Oxygen wants 8, nitrogen wants 8, oxygen wants 8. We would like to have 24 electrons. Unfortunately, we only actually have 18. We can do that subtraction. 24 minus 18 gives us 6 electrons that are in bonds. We started with 18 electrons, 6 of them are in bonds. The other 12 electrons have to be in lone pairs. Now we know what types of electrons we have. We can start to fill those in. 6 electrons in bonds. Make sure that every atom is connected to each other. That's the whole point of having a molecule. Those 2 lines account for 4 electrons. We want to have 6. So we're going to need to draw one more line. For our lone pair electrons, we need to make sure that every atom has access to the number that it wants. This oxygen on the left, it wants to have 8, but right now it only has 2. Let's start adding more electrons until we get up to 8. Our nitrogen in the center, it wants to have 8, but right now it only has 6 electrons. Let's add some lone pairs until we get up to 8. This oxygen on the right would like to have 8 electrons. Right now it only has 4. So let's keep adding 5, 6, 7, 8. To check, we can count up, do we have the right number of total valence electrons? Do we have an octet on every single atom? The answer here is yes and yes. One extra wrinkle here, since we have that negative charge, we also want to have a negative charge on our Lewis structure. The charge goes at the top right. That negative charge, it looks like it's suspiciously the same shape as a bond. So let's make sure that it's not confused for a bond. Let's put it outside of some brackets. There we go. This is our good final answer. NO2 minus has a Lewis structure like this. That's where the electrons are in this molecule. We have some practice questions here. Take a moment, grab your pencil and paper, write down the best answer you can get. This strategy that we've introduced and gone through a few times, it works when our atoms follow that octet rule. Unfortunately, there are some exceptions to the octet rule. Sometimes we have an odd number of electrons. Sometimes we have too few electrons around an atom. This is an incomplete octet. Oftentimes this is with boron, which is happy with 6 electrons instead of 8. Or we can go beyond the octet and have 10 or 12 electrons surrounding some atoms. Here we have sulfur and phosphorus. This is possible when we have elements that are low down on the periodic table. For us, we'll try to stick to molecules that do obey the octet rule, and so we can follow those rules that we outlined before. One last piece to consider to complete our Lewis theory discussion is this idea of resonance. Sometimes we can draw multiple Lewis structures that are equally as good. We have a prompt here. Can we draw the Lewis structure for SO2, sulfur dioxide? Take a moment, see if you can draw your version. Some of you might have drawn this molecule. At the same time, some of you might have drawn this version of the molecule. Both these versions look equally good to me, and so, well, which one's right? What actually happens? What do we see in real life? We need some way to deal with this in our Lewis theory. The answer is that, well, both of these Lewis structures are good to draw, but neither of them is what we see in real life. What we see in real life, if you have multiple good Lewis structures, is something that is in between those two drawings, or in between those 3 or 4 drawings. The fun analogy that we can use is to think about a rhinoceros. If you were trying to describe a rhinoceros to someone who didn't know what it was at all, you might try to make a comparison. You could say a rhinoceros is like a combination of a unicorn and a dragon. Our rhinoceros is horned like a unicorn, but it has that thick, leathery skin like maybe a dragon. If you describe your rhinoceros this way, it's a nice visualization of kind of what it could be as a combination of things. But when we're thinking about the rhinoceros, is it sometimes a unicorn? Is it sometimes a dragon? Are these rhinoceroses a herd of some unicorns and some dragons mingling together? No. Our rhinoceros is its own unique thing. We're just using those other animals to describe how it might look like. Moreover, our unicorns, well, they're not really going to exist, unfortunately. And our dragons, those don't actually exist either. Those aren't real life things, those are fantasy. However, the combination of them is like our rhinoceros, which is what exists in real life. This is how we're going to use our resonance structures as well. There is something that exists in real life, but it's hard for us to draw it with our Lewis structures. Instead, we'll draw things that don't really exist, but the combination of them add together to make a good visualization of what does exist in real life. Our plan for these resonance structures, well, if you have double bonds that you could put in multiple good places, let's draw every possible combination and separate them with double-sided arrows. This shows that all of these are equally good possibilities, and what actually shows up in real life is some mathematical average of those things that we drew. All right, we can pull this all together with an example here. Draw our Lewis structure for nitrate, including all resonance structures. I've outlined our strategy here to get a Lewis structure. I figured out we need 8 electrons in our bonds, 16 electrons in our lone pair. Don't forget this minus charge adds an extra electron to our valence electron count. I've drawn one version of this. We need to have 1 double bond and 2 single bonds to get our 8 electrons in bonds. I chose to draw that double bond to the top oxygen, but actually this isn't the only choice. We could have drawn it to other places. So actually we're going to need to draw some resonance structures. Let's draw all the versions that are good. Here are the 3 choices. Let's list them all out and separate them with some double-sided arrows. The last little detail, we do have some anion action here. Let's add in that negative charge and let's put it outside of brackets so that it doesn't get confusing. All right, we've introduced Lewis theory, and now we can determine the connectivity of the atoms in our molecules, including the types of bonds that exist and the number of lone pairs on each of our atoms. Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.